Good morning. My name is Marie and I work for L'Avion Jaune. And today I'm going to talk about an interesting project of erosion monitoring using LiDAR systems. So first of all, who is L'Avion Jaune? So L'Avion Jaune is a company which was created in 2005, and the main activity was first developing fixed wings for aerial surveys. In 2010, we achieved the first major mission with fixed-wing drone, and it was in French Polynesia. And then in 2012, we tried our first drone LiDAR prototype, and 3 years later, we created YellowScan to continue the drone LiDAR development and production. So we can focus on aerial survey, which was what we like more. And in 2016, we started to develop instruments and payloads. And in 2021, we concluded some drone and software distribution agreements. So all along these years, we carried out hundreds of aerial mapping missions with various kinds of sensors and vectors. And we carried out R&D projects and survey in France and abroad. We are now 8 people working at L'Avion Jaune, and there are more than 60 people at YellowScan. So we offer 3 kinds of services: aerial survey, payloads and instrumentation, and remote sensing. So this is our fleet of vectors. We work with various vectors and sensors. We have a light aircraft, some fixed wings and multi-rotor UAVs. We have professional cameras for photogrammetry. We have thermal sensor, and we use LiDAR scanners. So depending on our client demand, we choose the best combination of vector and sensors. So from our aerial operation, we can produce 3D point clouds, orthophotos, digital surface model, digital terrain model. And from these data sets, we can also produce classification, vegetation index, mesh, topographic maps if required. Payload and instrumentation. I will go fast on this one. So L'Avion Jaune has designed an innovative mapping systems, and this system can produce a map in less than 4 hours. And we are reseller for quantum products, Trinity Pro and Cube. And we also are reseller for photogrammetric software, which is Correlator 3D. And for the remote sensings, and we have developed some image processing algorithm using artificial intelligence it's mainly for agriculture use. So aerial survey services and products are useful for a wide range of applications like ecology, marine environment, industry, geohazard, management, agriculture, archaeology. And now we will focus more on geohazard management. So how can LiDAR contribute to coastal erosion management? Customer. So the customer is the French Mining and Geological Research Center, the BRGM. And the context, we are southwest of France on the Atlantic coast next to the Spanish border. It's the Basque coast, which is a rocky coast, and it's particularly urbanized and exposed to rockfall and erosion hazard. The challenge was to monitor the rocky coast movements during the equinox tides over 3 years. And the study area was 2 areas which was particularly prone to erosion, Bidart and Sokoa. The mission challenge, so the customer required a detailed topographic description to understand erosion processes and define an erosion plan management. He needed a multi-year monitoring and a precise control of the acquisition dates. So for L'Avion Jaune, the concern was how to get the best result with the most competitive offer. We needed to choose the method, select the tools, and propose the deliverables. So first of all, the element we had to consider was what was the required data set, especially precision and accuracy, resolution, or point density, and in this case, the repeatability. Second point, to choose the vector, we need to know more about the area's configuration, access, topography, and frequentation. We have to consider the timing, in this case, the dates of equinox tides, the tides timing table, and the weather. So is it feasible? And last but not least, the aerial regulation to operate in these areas. So the deliverables technical specification are here. We needed a 2 centimeter resolution orthophoto. For the LiDAR, we needed 100 points per square meter, 5 centimeter precision, and 10 centimeter accuracy. And the client wanted 6 campaigns over 3 years. The area's configuration, so there are 2 areas. One is 2 kilometers long, the other one is 1 kilometer long. Wide, they are around 200 meters wide, and the distance between the 2 areas was 8 kilometers. So we have 2 small areas close to each other. The relief is steep, but it's accessible. There is a road, and it's a frequented area and urban area, but it's suitable for UAV operation. So we chose the YellowScan Vx-20 on a multi-rotor UAV. Here are the specifications. So this is a Regal Minivux scanner with an IPX20 from Aplanix. This is an infrared wavelength. The bathymetric green scanner was not available during the project, so this is only about topographic acquisition. And precision is 1 centimeter and accuracy 2.5 centimeters, so it will be okay for our study. Field of view, this is important because we needed the more precise description of the cliffs, so 360 degrees. And well, the first mission was in 2019, so this was the best YellowScan LiDAR solution at the moment. And for the last mission in 2022, we used YellowScan Ultra 2, and the result was also satisfying. So the regulation was one of the biggest challenges for this project. You can see here, it's the aeronautical map of aeronautic regulation map of the area. And here are the 2 study sites. So first, you can see this yellow area, which represent medium built-up area. So normally the minimum flight height in this area is 3,300 feet for airplanes, and for an UAV, the maximum weight is 8 kilos. Then we have the restricted R266 area, which extends from the ground to 2,000 feet. And BRGM area is in the control area of the Biarritz airport. And here you have the map of the restriction for UAV flight in France. And red area basically represent areas where you can't fly unless you ask for a specific authorization. So as you can see, this is quite a challenge to fly a drone in this study area. So I won't go into detail here, but we asked and we got the authorization from all the authorities. And we had to make a SORA, which is a specific operation risk assessment, which is a complex process with a various description of all operation, flights, parameters, and so on. So we succeed in get the authorization, but we had some flight constraints. The drone has to be equipped with a parachute. We had the maximum speed. We could not go faster than 2 to 4 meters per second, a maximum height of 30 meters, and horizontal distance from the road was 30 meters. And we had another limit, is that we had to anticipate the mission date around 2-3 weeks to contact all the authorities and make sure we had all the authorization for the day. So now we are allowed to fly. So how do we fly there? We had to fly at the tides with the biggest coefficient, so ideally the equinox tides. So we have to check the calendar and see the date of these tides, then get all the authorization, okay. Hope that the weather will be good enough to fly on the day, so low wind, no rain, and ideally uniform light for photogrammetry, but this, it was like not the most important. And we had only 2 hours around low tide to fly. So it was tricky, but it's feasible. And for the flight plan, we needed to respect flight speed and height, distance to road and houses, and we wanted various scan angles so we can add some points, even if the small cavity and inside the cliffs. So this is the configuration of BDAR area, and this is the flight plan we choose. So there is a classical flight plan which is parallel to the coast, and then we made another flight plan following the cliffs and the more intern, and the flight line next to the city has to respect the distance to the houses, except for those ones, because we met the owner and they allowed us to fly there. And for SOCOA, we wanted some points inside the cliffs and caves to describe the structure, and this was a bit more tricky. So this was the first mission flight plan, but we were not really satisfied with the penetration into the caves. So then we tried this kind of flight plan. So this flight, we always done it, and then we try from various scan angles. So you have the flight 2 in red and the flight 3 in blue. And finally, the best flight plan was this one. So the first one is a classic design. The drone is following the flight line, as you can see the yellow sets. And on this second flight, we define a fixed heading. So the drone was following the flight line, but the front was already heading this way, and it was moving laterally. And then for the third flight, we moved the heading. So with this flight plan, we had the best penetration into the cliffs. So acquisition and processing. So it's just to show you how it looks like. So the point was to get some points in these dark areas inside the cliffs, because the researchers are interested in how the waves would erode these rocks. And here are a few pictures of the field operations. So here you have my colleague collecting ground control points. In the middle you have the drone with his parachute, which is this small cylinder here. And in the right, the takeoff and landing delimited area. So we carried out 6 operations. For 5 of them, we used Vx-20, and for the last one, we used the Ultra 2, and we get a better resolution. On the field, we collected more than 40 ground control points to check the precision. We follow a classical LiDAR processing workflow. During the field, we installed a GNSS base station, and we used PostPack for trajectory processing. We exported the point cloud with Cloud Station. And strip adjustment and classification were conducted in TerraSolid, as well as the production of digital elevation models. And one point which was important in this case, because we have multi-year campaigns, it's that we check, and if we need it, we correct the remaining shift between the datasets from the different campaigns. And for that, we use Cloud Compare. The deliverables, so classified point cloud, 100 points per square meters, 5 centimeter precision, 10 centimeter accuracy. So here are the DTM, BIDAR, and SOCOA. And now the scientific results. So all we produced were 3D point clouds from LiDAR and photogrammetry. The benefits of LiDAR is that there is height points and ground points, even below vegetation, and including in dark shaded areas where photogrammetry is not so good. Photogrammetry, we have a better density, so we have 1 point each 2 centimeters and the color, but we have no points below vegetation. And then we also produce DSM and DTM from photogrammetry and LiDAR and orthophotography. And from these datasets, the researcher from the Geological Research Center produced some derived products, included shaded DTM, roughness and slope maps, and they calculated point close distances or made raster differences. So what I will present you from now is the work of Clara Levy and Thomas Dewey from the BRGM. So first of all, they made qualitative comparison to study the landslide dynamics. So for example, here they identify fault support erosion, regressive erosion here, the destabilization of the rock block slide, and surface degradation of the back rock block. Another quantitative measure, they made quantitative measures. For example, here is profile analysis. So on a profile, when they detected a free line, they then fit a plane to the deepest visible rock layer, and then they measure a distance from the point cloud to this plane. And doing multiple profile of this distance, they could produce a map of instability. So they have this map of instability for one date, for example, June 2019, and then they could quantify erosion by point cloud distance between the campaigns. And what they highlighted was that the major instability areas corresponds to some real erosion areas observed between 2019 and 2022. Thanks to the qualitative approach, to the cloud-to-cloud distance erosion measurement, and to some additional field measurements, they were able to describe the erosion processes. So first of all, they identified that the first block will slide, so this is plucking phenomenon. Then the wave will come inside the cavity, and the structure of the rock will change, so this is plucking. Then the wave exports the rock blocks, and finally, this block will slide on the other one. They also produce some slope rasters, and they identify the profile with specific variation of steepness. So there is first a flattening and then a steepening. So they could identify buckling 1 year before the rock would be exported. So in a conclusion, so the customer required detailed topography description to understand erosion processes and define an erosion management plan, multi-year monitoring, and control of acquisition date with various constraints. L'Avion Jaune report, so that was a complex management of authorization with local authorities, and we produced dense LiDAR and photogrammetric point cloud, some digital elevation model, and a great multi-year dataset. And so what was learned from these datasets? So they could describe the destabilization processes, plucking, buckling, block slides, measure the erosion intensity, and they could produce instability indices for the prediction of erosion. Okay, thank you for your attention.